Well. This is day 22 of doing math problems until a Hololive member notices me. And pretty much today we're pretty much going to go ahead and look at this pretty beautiful sum that converges to pi over 4. And how do we prove it, right? Well, it's fairly easy, right? If we simply just go ahead and look at just one trigonometric function, the tan inverse of x. Because we know that tan inverse or arctangent of 1 is pi over 4. So we're going to use that to our knowledge, and we're going to make a Taylor series or Maclaurin series. So we have f of x is equal to that, and f prime of x is equal to 1 over x squared plus 1, and then f double prime of x is equal to, and the quotient rule of this, or we'll just take the derivative, which is x squared plus 1 to a negative 1. Taking the derivative, we get negative times x squared plus 1, negative 2 times 2x. So we end up with 2x over x squared plus 1 squared. And so on, right? And we're going to center it at, let's say, 0. Okay? And pretty much if we go ahead and center it at x equals 0, we're going to have that pretty much our Taylor of x is going to be pretty much f of 0. So we'll have 0, and then it will be plus, and then since that is 0, we will have 1 over 1 factorial, right? And then it's going to be x, and then plus, and then the x is 0 in the numerator, so we have 0 over 2 factorial x. And let's check for the third derivative, right? So we have f triple prime of x is equal to, and that derivative is going to be one nasty one. So let's go ahead and do it. So we have to use the quotient rule, which we will have the denominator is going to be x squared plus 1 to the 4. And then we're going to take the derivative of 2x, which is going to be 2, and times x squared plus 1 squared minus 2x, and then the derivative of the denominator, which is going to be 4x times x squared plus 1 times 2x. And since x is 0, right, we're going to also have right here that it is the x's cancel, so this cancels out, this cancels out, this cancels out, just leaving negative 2. Negative 2 over 3 factorial x cubed. And we might notice a pattern, right? We're pretty much going to see that for every even derivative, it's always going to result in a 0, right? So we could say that the next term is just going to be an x to the 5th term. So we could rewrite this as plus x, and then plus, or actually minus 1/3, right? So it's going to be 1 over 3x cubed. And of course the next term is going to pretty much be plus 1 over 5 x to the 5 minus 1 over 7 x to the 7. And we see a recurring pattern, right? So let's try to make a series off of this, right? Pretty much we know that our sum from n equals 0. So let's go ahead and look at the changes in the signs first, right? It starts from positive, and then negative, positive, negative. So that is going to be -1 to the n. All right, because for n equals 0, we get a positive, and then for n equals 1, we get negative, n equals 2, even, 3, negative, and so on. And the degree changes in degrees of 2. So we have x to the power of 2n plus 1, because for n equals 0, we get 1, and for n equals 1, we get 3, for n equals 2, we get 5, and so on. And of course, the denominator, right, we are going to see that it just changes in the same degree, right? The denominator is 3, the degree is 3. So we see the denominator is equal to the degree. So we could rewrite this as 2n plus 1. So we could say then that tan inverse of x is pretty much equal to this series, right? And if we plug in tan inverse of x equals 1 and say this, we get that the series then becomes from n equals 0 of -1 to the n. And then since x is 1, everything disappears, and we get 2n plus 1, which results in pi over 4 is equal to our sum. So we can see that pi over 4 is equal to 1 minus 1/3 plus 1/5 minus 1/7 plus 1 over 9 minus 1 over 11, and so on. So yeah, that's pretty much a cool way to rewrite pi over 4 as a infinite series. So hopefully you liked it and enjoyed watching this and noticed how beautiful all of this looks. Right? It doesn't take rocket science just to do this, but it does make it fun to learn cool things like this. Right? You could express a irrational number as a series, as an infinite series at that. So yeah, thank you for watching, and with that I say bye bye.